Right. Yesterday, as I said a couple of times, was introductory. Today we shall start with the real business. Yesterday we have seen that multivariate analysis techniques are needed or are not available, which can be used on large data sets, where large mainly refers to the number of variables, can be used on data sets with a mixed measurement level, by which I mean that some variables may be categorical and some variables may be numerical, and can be used on non-random data, by which I mean that these data are not necessarily the result of a random sampling process. Today we shall be building a system of multivariate analysis techniques that in the first place has the existing familiar linear multivariate analysis techniques as special cases. And by the existing familiar linear techniques, I mean principal component analysis, canonical correlation analysis, multiple regression, discriminant analysis, analysis of variance, both univariate and multivariate. These are all special cases, but in addition, it has many other possibilities, many other options, many other techniques as special cases, notably techniques filling the gap that is described up there. The system is built around the notion of homogeneity, which I shall define in a little while, and around a particular least squares loss function which must be minimized. So all the techniques in the system can be seen as particular cases of the results that you get when you minimize a certain loss function. And there are of course variations, for instance in terms of the restrictions on the parameters, or in terms of choice of dimensionality, or in terms of number of variables or number of sets of variables, and these variations define the various different techniques. Techniques will be discussed both from the geometrical point of view, that is familiar to people working in multidimensional scaling, from the algebraic point of view, which is in terms of eigenvalues, determinants, and things like that, which is perhaps familiar more to people working in multivariate analysis in the statistical sense of the word, and also from the statistical point of view, by which I mean that at least some of their sampling properties, whenever those things can be applied, will be discussed. This is more or less summarizing. There's one thing I perhaps should say at this point. The idea of taking homogeneity as a central notion of the class of techniques is relatively new, by which I mean that it is not literally and with that much emphasis in Gifi. In this sense, the talks I'm presenting here are sort of a later stage of developments. In your reference list there's a paper in the Data Analysis and Informatics volume edited by Edwin Dide. And the paper is by me, and it's called Gifi System of Nonlinear Multivariate Analysis. In a sense, that is a more up-to-date version of the Gifi system than Gifi itself. But the paper is exceedingly brief and perhaps rather cryptical. So this is more modern, but less well documented. Right. Quantification and coding. From yesterday we remember that we were dealing with multivariables, another word for sets of variables, for a number of variables, m variables in general. These multivariables had a common domain on which they were defined, and they had possibly different ranges. We shall talk for the moment about a special case in which the range of these variables is finite, and in which the domain on which they are defined is also finite. Now, generally it's easy to generalize this to situations in which you have infinite domains, for instance if you're dealing with random variables. But this is what I called yesterday specialization, and you'll find the details in the books, but it would take us too far, I think, in this particular seminar to go into them. The fact that these domains have the same number of categories is not very essential. I only use it to simplify the notation, otherwise I would have to give this k here an index too, and I would mean double indexing, and that would be not very nice. Of course, you can always suppose, if you have a finite number of variables, that all variables have the same number of categories simply by adding categories which happen to be empty. So that's no real restriction of generality. The fact that I suppose that the domains consist of the first k integers is also no restriction of generality, of course. If they happened to be Protestant, Catholic, and Buddhist, then you simply have to decide beforehand that you're going to call Catholic 1, Protestant 2, and Buddhist 3 in some order. The technique in itself is independent of the order. That is at least in the version that I will talk about now, of the order in which you choose your coding. So it's merely a question of coding. You have to code them anyway if you want to feed them into the computer. So we choose this particular coding, 1 to k. Concept of quantification. A quantification of the objects or individuals is a mapping of the domain of variables into p-dimensional space. I'll get this chair out of the way. This means that we assign a vector of p real numbers to each individual or object in the domain. The number p is the dimensionality of the quantification. So a quantification simply means you have a number of animals or rocks or whatever the objects of your study are, and instead of labeling these animals and rocks with some sort of verbal labels, you now assign a vector of p real numbers to them in some way. And of course, any assignment of numbers to these objects is called a quantification. We will be dealing, of course, the technique will be about optimal quantification, about how you should proceed in assigning these numbers, and not about arbitrary quantifications. This is the definition of the quantification of the objects or individuals, of which you have n. It says m here. That's a horrible error. It should be n, of course. There are n individuals. Similarly, and you could say dually, we also define a quantification of the categories of a variable, or sometimes shortly the quantification of a variable, as a mapping of the range of the variable into the p-dimensional real numbers. Again, p is of course the dimensionality. So each variable has a domain and a range. Quantification of the domain is dealt with here. Quantification of the range means that each category of the variable, for instance, Protestant, Catholic, Buddhist, is mapped into the real number. So you have Protestants -1 + 1, Buddhists 0, 0. In that case, you're using two-dimensional quantification of the categories of the variable religion. In some contexts, you do not want to use the word quantification, but you want to use the word transformation. That's important because it's more familiar to some persons, perhaps. If your original variable was a numerical variable, and you assign new numerical values to the category of your variable, then you're dealing with a transformation. It would be more appropriately called a transformation because you had a real valued variable to start with, and you wind up with a new revalued variable, and in that sense you have transformed it. In that case, of course, it's usually the case that p equals to 1. So you have a one-dimensional quantification, and in the context of numerical variables, that's often called a transformation. So another way of putting it is that we'll be dealing with optimal transformations. But for categorical variables, of course, such as this religious variable, transformation doesn't make much sense, and quantification is a better word, I think. Well, let us first define what we mean by a perfect quantification, understanding also perfectly well that perfect quantifications will not be very relevant in practice. I've already mentioned optimal quantifications. That is what we will be aiming at. But in order to define optimal, we first define perfect, because optimal will be defined as being as close to perfect as possible. That's logical. A quantification of the objects x, well, the objects are, of course, the set omega, but the quantification of the object is a matrix x, a matrix of n rows and p columns, where row I refers to the quantification of object I, and that's the row I is, of course, xi. Such a quantification is perfect if, for all I, j, and k, the mapping of the value of that object on variable j is equal to the value of the variable on object k. If that is the case, then the quantification should also be the same. So if two objects are in the same category of a variable, then they should get the same quantification. All Protestants should have the same quantification, and all Catholics should have the same quantification. If objects which are in the same category of a variable have the same score, we also call that a score if it refers to objects. Object score. This is somewhat more complicated, but equally, I mean, it looks complicated if you write it out, but if you read it in words here, it's real simple. Quantifications y1 to ym of the variables, remember that you had m variables, each with k possible values. So quantifications of a variable define a k times p matrix. There's one such k times p matrix for each variable. The matrix for variable j is called yj, and these are the m matrices for each of those variables. So these are the category quantifications for each of the variables. Now these quantifications are perfect if the quantifications corresponding with the values of each object are the same. Now that means if you have more than one variable, for instance you have religion and you have length, an object gets a quantification from the religion variable because you have quantified the religion categories. An object gets a quantification from the length variable because you have length categories which are quantified. And the requirement here is that that particular object should get the same quantification from the religion variable as from the length variable. I will show that with an example. This is a small example of a data matrix, not a real one, of course. I just made it up. It's also one which is used in the introductory chapters of Gifi, so I just didn't make it up for the occasion. There are 3 variables and 10 objects. Variable 1 has 3 possible values. Variable 2 has 3 possible values. And variable 3 has just 2 possible values. They're coded here, A, B, C, P, Q, R, and U, V. So this could be anything, but they're coded in this particular way. Now the requirement that a set of object scores, X, which is a 10 times P matrix, and I don't specify P here because it isn't necessary. The requirement that a set of object score is perfect is that the x of 1 must be the same as that of 3 and of 4, of 7 and of 8 and of 10, because they're all in the same category of variable 1. And the same way, that's listed over here, the same way the quantification, the score for object 2 must be the same as the score for object 5, because they're both in category B. Yes?
Are you using the word perfect then to mean discrete quantification?
Yes. Yes. Ties, if something like ties is defined, I mean, I've not defined ties because I'm not necessarily talking about numerical variables. Ties are not broken. Everybody who is in the same category gets the same score. That's discrete in your terminology. And also, the score of object 6 must be the same as the score of object 9, because they're both in category C of variable 1. Now, a similar list of requirements from column 2. Everything that's in category P over here must get the same score. That's a very long list. And the fact that everything in category Q must get the same score does not add any information to the list, because there's only one object in category Q. Same for category R. And there's a similar list of equality restrictions from column 3. Now, of course, it becomes obvious from this list why it's not useful to look for perfect quantification. Because if you take all these equality restrictions together, then they will dictate, of course, that all object scores, all scores for all objects should be the same. And that's not very interesting in terms of quantification. So the only solution that is left is a trivial solution in which everybody gets the same score. Now that's perfect quantification, but it's not very interesting because it's not dependent on the data, or only marginally so. Perfect category quantifications, remember that there are 3 variables with 3 categories each, and they get quantifications. The y of A is quantification for category A, the y of P is the quantification of category P. So the perfect category quantifications must satisfy restrictions like the y of A must be equal to the y of P, and that must be equal to the y of mu, because these 3 categories all correspond with the same object. And row 2 gives you these restrictions here, because object 2 has categories B, Q, and V. So this gives you a very long list. There are 10 such equality type restrictions. This gives you a very long list of restrictions on the y's. And again, I haven't checked it out, but it seems rather obvious that the only solution to these equations is YA is equal to YB is equal to YC is equal to YP, and so on and so forth. So the only perfect quantification that is possible in this example is the trivial one. And this is a small example, so for large examples it will even be worse. This is what I said at the beginning. Perfect quantifications are not really interesting because you do not expect to find them in practice. The concept of perfect quantification can be explained also in matrix algebra, matrix notation. For this you need the notion of an indicator matrix. The indicator matrix is defined on this transparency. The indicator matrix of a variable, each variable has its own indicator matrix, is an n times k matrix G of Gj, because we're defining it now for variable j. And it consists entirely of zeros and ones. And it has a 1 and exactly 1, 1 in each of its rows. So for the small example we had, which was this, the indicator matrix for the first variable is given here. It's a 10 times 3 matrix because n is equal to 10 and k is equal to 3. And the ij element of this matrix G1 is equal to 1 if the object is in the category in this corresponding row and column, and it's equal to 0 otherwise. So everything which has an A here gets a 1 in the first column there, and everything which has a B gets a 1 in the second column. Now this immediately shows why all rows add up to 1, because everything has to be in at least one category, exactly one category. There's other property here listed which is, I'll remove this, which is easy to understand. D of J, which is the inner product of G with itself, the cross product, is diagonal. If you compute products of these columns here, then there's no column which has no pair of columns which has 1 in common. The categories are exclusive. That's another way of putting it. Consequently, this matrix D, I use primes for transposes, is diagonal. On the diagonal of D, you find the number of 1s in the corresponding column, which are the univariate marginals. There's also the cross product of two different indicator matrices, which is interesting. And for that I use the notation CJL. This is the cross product of the indicator matrix of variable J and the indicator matrix of variable L. This CJL is the bivariate cross table of the variables. So if you compute the cross table of G1 and G2, this is the indicator matrix of the second variable, then this gives you the 3 times 3 bivariate cross table of the two variables, within each cell indicating how many there are in, for instance, in category A of variable 1 and category Q of variable 2. We call this, by the way, a complete indicator matrix because all rows add up to 1. So obviously there's also something as an incomplete indicator matrix, which I will come to later. But for the moment we have complete indicator matrices. This structure up here, which simply consists of the indicator matrices of all variables next to each other, is called the indicator supermatrix in Gifi, and it's the symbol is simply G without any index. Now this is of course familiar from many different sources and disciplines, as dummy variable coding, design matrices in analysis of variance. They all use the same type of coding of categorical variables. Of course, we use this coding for all variables, at least in this technique, because we don't care whether the variable was originally numerical or originally ordinal or originally categorical. They're all coded in terms of indicator matrices. There's a couple of pages here from Gifi, which show you the same example again. This is the data matrix as I have just copied it on my transparency. This is a way in which you sometimes also find it. Simply all the possible combinations of categories are listed and their frequency is indicated. This is called the profile frequency matrix. And we've already encountered this in this Japanese religion example that you may remember from yesterday, with 6 binary variables. In this case, 3 ternary variables, if that's the correct expression. There are 27 possible answer patterns. The reduced profile frequency matrix you get from this one by deleting all zeros. Let's see, all patterns with 0 frequency. You have this here. That's also a familiar way of coding this data matrix. And another familiar way of coding is as a high dimensional, in this case a 3-dimensional contingency table that's given down here. Of course, this contains the same information as this and this and this. It's just 3 ways in which you meet this matrix in various applications and in which you can make it ready for various types of techniques. For our technique, at least for the technique we will be talking about today, you need to make it, or to give it the form of a indicator matrix, which again is listed for this example up here. The same indicator matrix that was on my transparency some time ago. This is G. The inner product of G with itself is called C. It consists of submatrices where each submatrix contains one set of bivariate marginals, one cross table. So this here is the cross table of variables 1 and 2. This is the cross table of variables 1 and 3, and so on. And the diagonal of C, which is listed here again, is D. And on the diagonal of D you find the univariate marginals. Observe that in this example there's one category which does not occur. So here I did use the trick of giving them all the same number of categories by defining a sort of an empty category for the third variable. The thing below here need not concern us. So this is the concept of an indicator matrix. We have now discussed coding, we have discussed perfect quantifications, and we now shall link the two concepts. This is a quantification of the categories of variables 1 to m. Such a quantification is perfect if there exists a matrix of object scores, a matrix of object quantifications, such that this is true. The gy1 is equal to, and so on, ym is equal to x. In other words, if and only if these matrices here are equal. Now this is just a matrix formulation of the, let's say, verbal or logical definition of perfect quantification that I gave before. And it's a matrix formulation by using the concept of indicator matrices, which is a well-known way to code logical or categorical information. There's a similar definition down here. Again, this is sort of dual to the previous one. I'm using dual in a sort of informal way now. Actually, this corresponds with the familiar duality of linear algebra. And I don't know in how far I will mention that later on in a more technical way. But there's a dual definition of perfect quantification of the objects. And it looks exactly the same, but here the requirement is that there exists a corresponding system of object scores such that this equation is true. And here you define x to be perfect if there exists a corresponding system of category quantification such that exactly the same relationship is true. In summary, you can combine the two and say that a set of quantifications of both object and categories is called perfect, and perfect can also be called perfectly homogeneous, because that's the concept of homogeneity that we're trying to define, if this very same set of equations is true. So you have 3 times the same set of equations. In this case, you're merely defining perfectness of y by saying that there must be an x such as this is satisfied. Here it's the other way around, and here it's symmetric. It's a subtle difference, but it is different. Now, you can manipulate with these definitions and derive some small theorems. First, we will manipulate the first definition and sort of eliminate x from it. And if you do that, then you get the result that a set of category quantifications is perfect if and only if all these matrices are equal to their average. This is one form of saying exactly the same thing. I mean, they're perfect if and only if there exists an x such that this is true. Well, if that is the case, then the average certainly satisfies these restrictions. So if and only if it's equal to their average, and if you translate that into products of matrices, you get the relation down here, which says that these two matrices must be equal. Now this is perhaps not immediately obvious, but it's familiar from analysis of variance. This is the total sum of squares of the category quantifications. And this is the between variables sum of squares of the category quantifications. So again, I'm saying that this set of quantifications is perfect if and only if there's no within variable variance. In other words, if and only if all rows of the matrix in which you have replaced the labels by scores are exactly the constant. So each row only contains the same numerical values or the same vectors if you have replaced the labels by quantifications. So this is the analysis of variance formulation of perfect homogeneity, perfect quantification. And again, there's a dual definition which I prefer because it's usually more easy to visualize. I've eliminated now from the second definition that was given up here the y's. This is the second definition. X is perfect if and only if there exist y's such that this is true. Now you solve for the y's and you find the theorem up here. X is perfect if and only if X satisfies these equations up here, where the P's are now defined as matrices of this form. And these are orthogonal projectors which project on the space spanned by the columns of G. So what this part of the projector does is take averages over all categories, over the categories, and then it expands it again to an n times P matrix. So this projects X orthogonally on the space spanned by the columns of G. And you can again translate this, as in the previous theorem, to cross product conditions, and you find that you must have x prime x equal to x prime p average x. P average is the average of these projectors. And again, this can be interpreted in terms of the total sum of squares of the object scores must be equal to the between objects sum of squares of the object scores. And again, this is just one way of saying that objects which are in the same category of a variable must have the same object score. So what we're actually doing is we're translating these logical concepts into matrix algebra, and we're getting, by this translation process, we're getting closer and closer to something which can be used to define optimal homogeneity instead of perfect homogeneity. Another way of putting it, which is even more close to optimal homogeneity, is that X is perfect if and only if the P largest eigenvalues of P star are equal to +1. Remember that P star is the average projector, which means projectors have eigenvalues which are between 0 and 1. Average projectors have eigenvalues which are between 0 and 1. X is perfect, well, it says the same thing over here, if and only if the P largest eigenvalues of P star are equal to +1. And Y is perfect if and only if the P largest generalized eigenvectors of C, of the pair C and MD are equal to +1. This is the C and MD come from this relation at the bottom here. Which correspond with the eigenvalue relation for the average projector. So, first formulated in terms of indicator matrices, then formulated in terms of matrix relationships, and now formulated in terms of eigenvalues of certain matrices that can easily be computed and that can easily be interpreted. This average projector, of course, is familiar from discriminant analysis, for instance. It gives you the between sum of squares, between group sum of squares for each variable. And this C is the matrix of bivariate marginals, which is, in the French literature, it's called the Burt table. And it contains the cross tables of the various pairs of variables, and consequently is also a familiar object. It's perhaps not familiar to organize your cross tables into such a matrix, but the components are certainly familiar. And D are the univariate marginals. They're also familiar. Now here in blue, it says perfectness cannot be attained for real data sets. That's sort of obvious. We've seen that already in the logical formulation. It's also clear from the eigenvalue formulation, of course. Thus, we look for optimality. Now, looking for optimal quantifications instead of perfect quantifications defines homogeneity analysis. So now we're real close to the definition of homogeneity analysis. We just have to define optimality, and of course, the presentation already implies that I'm going to define optimality in terms of the eigenvalues of these matrices. First, yeah, this is very difficult to read. Yeah. First, we will start with something which is very obviously a direct measure for the perfectness of a quantification. It's raining. Measuring departure from perfect homogeneity of given scores and quantifications. Given scores X and quantifications Y. What you do is you take the definition in terms of X must be equal to G1, Y1, G2, Y2, GM, YM, and you simply translate that into a least squares loss function. You take the sum of squares of the differences. Trace is the trace operator, so trace X prime X is the sum of squares of X, and trace residual primes residual is the sum of squares of the residuals. Now this is the loss function I was mentioned earlier, on which the Gifi system is built as a starting point. In homogeneity analysis, we want to find X and Y in such a way that this loss function is minimized. That's briefly stating the purpose of homogeneity analysis. In black, in between here, there are a number of names by which the technique is also familiar, and maybe even more familiar. So I think I should mention them. I can also make some historical remarks. The first one to propose homogeneity analysis under the name of quantification method was Goodman. That's the G here. That's Louis Goodman, not Leo Goodman. Louis Goodman in 1941 in a paper which is somewhat difficult to obtain but which really exists. He derived the technique in a one-dimensional case only and using correlation ratios, which means basically using analysis of variance terminology. So the way we present homogeneity analysis is, I think, merely a streamlined version of the way Goodman presented it in 41. There's another paper by Fred Lord. I think it's 1960. The correct reference is undoubtedly in Gifi. It can also be 1959 or something. And he calls it Goodman's principal components of scale analysis. So that's one name under which the technique is known. It's also known as factorial analysis of qualitative data. There's a paper by Cyril Burt, 1950, in which he describes the technique. And he introduces it in a completely different way. He says, well, I have this cross-product matrix C, which is a cross-product matrix, cross-product of the G's. And it's perfectly legitimate to apply factorial analysis to cross-product matrices, so let's apply factorial analysis to C. That's the way in which he introduces it, which is not really very satisfactory, very enlightening, but he did it pretty early. he had a nice example, and he had this C matrix in his paper, which is the reason why the French call this C matrix the bird table. This is the same bird that you may have heard about in other contexts too. There's also multiple correspondence analysis. That's the most familiar name perhaps, or at least perhaps it deserves to be the most familiar name. It's bound to be the most familiar name in the near future. It's the word used for the technique by Ben-Zakri's school, and it's described under this name in, for instance, in Greenacre's book on correspondence analysis. It's also called Hayashi's fourth method of quantification, which is not a particularly good name, I would say, but Hayashi introduced it, or, well, he didn't really introduce it. He sort of translated Goodman's work into Japanese, which is perhaps already a considerable achievement. And he published that in '56. So these are alternative names, and the problem, one of the problems with this class of techniques is that most people know it under different names. But what is in a name? It's all the same technique. Well, I said the purpose of the technique is to minimize that loss function, least squares loss function I gave on the previous transparency. I have to qualify that immediately because we obviously do not want a trivial solution x equal to 0 and y equal to 0 if you substitute that in the loss function, which is once again given up here. You substitute x equal to 0 and y equal to 0, you find sigma equal to 0, and 0, of course, is the minimum for any sum of squares. So you must not take me too literally when I say that we want to minimize this loss function. We do not want that trivial solution. Another trivial solution or a trivial dimension that we do not want is a dimension in which all x's are equal to 1 or equal to any constant for that matter, and all y's are equal to 1 or equal to any constant. If you substitute that particular solution into the loss function, then again you find that you have a perfectly homogeneous solution. And it is the one I was talking about earlier, the one that you also do not want. Now, in order to avoid these solutions, you need a normalization condition. I have written down two normalization conditions here. I'm using U for a vector with all elements equal to 1. So this one says that the columns of x should be in deviations from the mean, and this one says that the x should be orthogonal, and sum of squares equal to 1. And this normalization condition is a normalization condition on y. It says that the weighted sum of the y's should be equal to 0, and I'm now using y for a matrix in which all the y's for the variables are on top of each other. So y has m times k rows and p columns. M is the number of variables, k is the number of categories. And we also want y prime dy, which is the weighted sum of squares of the y's, equal to m. There's an m here times the identity. The reason why I use d here and not anything similar here, and why I use m here and not anything similar there, will become apparent, I hope, in not too long a time. There are two normalization conditions. Does it mean we impose them both or just one of them? And if we impose just one of them, which one do we choose? And what consequences does this particular choice has? Well, it states here that you only have to normalize either x or y. That's clear. If you normalize x, then you exclude all this triviality up here automatically, of course, because if x is normalized, then y is 0 is not a perfect homogeneous solution anymore, so you eliminate the whole pair by just imposing one normalization condition. Now let us see what happens if we normalize x. So we're going to minimize the loss function, the least squares loss function, with a normalization condition on x. It is perhaps I'll keep the loss function near at hand. I define sigma x star as the minimum of the loss function over y for fixed x, with y unrestricted. The minimum is attained for yj, category quantifications of variable j, equal to this expression over here. Now this is perhaps also very easily explained in words. This means that the category quantification given by this formula to a particular category of a variable is equal to the average object score or the centroid of the object score of the objects in that category. If you remember the structure of the indicator matrix, which simply selects from X the persons, individuals, objects, or whatever they are that are in a particular category, and then you divide it by the univariate marginal, which is the number of objects in that category. So this is simply the centroid of the object scores corresponding with the categories. So the minimum is attained for that. If you substitute that in the expression for the loss function, you get an expression which looks like this. I is the identity matrix, P star is our average orthogonal projector that we encountered before. And now we go from here to here. We now define sigma star star. The star thing is simply that I replace a variable over which we minimize. You replace that variable by star because it does not play any part in subsequent calculations. You've minimized it out. Now, sigma star star is defined as the minimum of the thing we have here, which we obtained by minimizing out y. But now we minimize with the normalization conditions on x. Remember, the normalization conditions were basically that x was orthogonal and standard unit length. Now, this means that you can use familiar eigenvalue results to show that the minimum is equal to p, the p comes from the identity here, minus the sum of the p largest eigenvalues of the average projector. Now, the p largest eigenvalues I said, but that's not exactly correct, because the largest eigenvalue of the average projector is always equal to 1, and that's exactly the eigenvector that goes with that is a vector with all elements equal to a constant. So that's the trivial solution you're trying to eliminate. Now this means, of course, because all other eigenvectors are orthogonal to this trivial solution, if there are no other eigenvalues equal to 1, which will commonly be the case, it means that the other eigenvectors automatically satisfy the condition that they must be in deviations from the mean, because they are orthogonal to a constant vector. So if you make the zero eigenvalue, the zeroth eigenvalue equal to 1, corresponding with this trivial solution, all elements equal, and you start counting from S is 1, you skip number 0, then this is true, and you have the sum of the p largest non-trivial eigenvalues there. Remember that you had perfect homogeneity if this one had p eigenvalues equal to +1, and of course that would make sigma star star exactly equal to 0. So perfect homogeneity is still defined in terms of this loss function too, as this quantity up here being equal to 0. Now, this derivation immediately shows you how to compute the solution of homogeneity analysis. That's one thing. Another thing is it gives you an interpretation. The x's are the eigenvectors of the average projector, and y is the centroid of the corresponding x. And what I mean by centroid is explained up here. In order to find, if you have found the optimal category, the optimal object scores, the x's, then it's very easy to find the optimal category quantifications from those optimal object scores by simply taking averages, centroids, of the objects in the particular category that you're trying to find a score for. This is in French the principe barycentrique, and we call it the centroid principle. which is a translation direct from the French. Again, you can also proceed dually. And if you want to proceed dually, you first minimize out x without posing any constraints on it. Now I do this real quick because it's sort of not very surprising where this leads. We have done everything so far dually, and we'll do this again dually too. And you find this expression up here, which is again very similar to this eigenvalue problem for D and C that we discussed earlier for the bird table. And then you minimize out y under normalization conditions, and you get an expression which is very similar to the expression we derived in terms of the average projector, but now in terms of the normalized bird table. Now that's one thing which is a little bit important, not very much. This is not a definition anymore. This is a result actually, because I'm using the same symbol here as a symbol I used earlier. It must mean that it's the same thing. But in other words, it must mean that the eigenvalues of the average projector, which were used here, are the same as the eigenvalues of the matrix which is down here. Now there's a small and not very spectacular proof of the fact in red here. We define the matrix H, which is equal to this. So it's indicator matrix normalized by the univariate marginals divided by the square root of the univariate marginals. If you define this matrix, then the average projector is equal to H prime, and the matrix in brackets here is equal to H prime H. And it's a well-known result in matrix algebra that the non-zero eigenvalues of H prime H and H prime, I should do the other way around, are the same. So this shows that it is true that this sigma star that I have defined here is the same as the sigma star that I defined earlier in terms of the average projector. And I can also show this in this little diagram up here. You start with a loss function, minimize it over x3 and it gets you there. Then you minimize it over normalized y and it gets you there. You can also go the other way around and you wind up the same spot. So this really tells you that it does not matter whether you normalize x or y. You find the same solution. You do find it via a different route, though, of course, and you do find it by solving a different eigenproblem. And it could be that one eigenproblem is simpler to solve than the other. Just a rapid one before the break. Oh no, the break is 4:10, isn't it? Okay. Just a slow one before the break. Homogeneity analysis computationally means finding the p largest eigenvalues of either the bird table, C, corrected for the marginals because we were not computing the eigenvalues of C, but of D minus 1/2, C, D minus 1/2, or the generalized eigenvalues of the pair CD, or computing the p largest eigenvalues of the average projector P star. And this eigenproblem is of the order m times k. I mean, it has m times k rows and m times k columns. That can be pretty big, of course. This eigenvalue problem is of the order n number of objects, which can also be quite big. Can be very big. So perhaps it's not a very good idea to try and solve these eigenvalue problems with one of the standard eigenvalue routines. Perhaps it's not a very good idea to compute these matrices at all if you want to solve a homogeneity analysis problem, because they can be very big. There are examples in my list of examples in which n is equal to 30,000. Now one wouldn't want to compute a 30,000 times 30,000 matrix P star and solve it and store it somewhere and then compute its first eigenvector. That would be a very wasteful way of proceeding. It says here pictures of loss, which this transparency is the introduction to the pictures of loss. And the idea of the pictures of loss is that it's very easy to show what the loss function measures geometrically. So I will now do that. This is a small cars example. It's not small cars, but it's a sort of a subset of the regular cars example that I understand that you're all used to. It's from the consumer's report, there are 10 cars. I selected 3 variables. This is their price in some unit, probably thousands of dollars. This gas consumption is the weight. I've categorized these data. I don't know which rule I use, but I know that this is the product of this categorization process. And I've also ranked them, but for this particular illustration, that is not very relevant. Now here is a picture in many colors in which I have a simultaneous representation of the variables and the objects. In this case, the objects are 10 cars. They're coded PH, DD, AE, DC, PP, BR. And for you, one of you may actually own a car like this, so I leave the list here. I think it will be fairly obvious which is which. CC, for instance, is the Chevette, and Dodge, Colt, Plymouth Horizon. They're sort of ranked. The idea is that this is sort of an arbitrary initial configuration, a sort of an arbitrary try at quantification. And the arbitrary try at quantification means that I've located the cars in these points in the plane. So I've chosen P equal to 2 and assigned two-dimensional vectors, pairs of numbers, to each of the cars. Now this arbitrary, I'm now going to check how good, how close to optimal, how satisfactory this quantification is. In order to... What? Yeah, well, yeah, my head, yes, wherever these quantifications come from. It cannot be random, that's clear. Perhaps I also looked at the data a little bit before I constructed the quantification. It's not one which is very bad, as we shall see. Now, the way in which this should be done, I first do it for the first variable. Everything in black here refers to the first variable. I compute averages for each of the categories. Remember that this is the discrete version of the data that we're working with. In the first category of the first variable, we find Chevette, Dodge, Colt, and Plymouth Horizon. So this is these 3 cars. Compute their average. That's the first try at category quantification. That's the first category of the variable price. Same for the second category, third category, fourth category. The fourth category has only 1 car, Oldsmobile 98. So it coincides, the car and the category coincide. It has a very good fit. The others do not have such a good fit because the black lines here indicate the size of the loss. Perfect homogeneity means that you want all these lines, you would want all these lines to be 0. You want all these cars to coincide with their centroids, which they do not do. So this is loss, the black lines, for variable 1. I've done the same thing for variable 2 in red. So there are now 3 categories, 1, 2, and 3 centroids, 1, 2, and 3. Category 3 of variable 2 only contains the DD and the AE, which are AMC Eagle and Dodge Diplomat. So that's a pretty good fit because they're not too far from their centroid, both. But category 2, which contains 5 cars, contributes much more to the fit because these 5 cars taken together are pretty far from their centroids. Oh, I'm pointing at a green one now. This is the one I would mean. Category 1 contributes a lot to the fit because the cars are pretty far from their centroid. In green we have variable 3, so that I could repeat the whole story for variable 3, but that's probably not necessary. Now this is a picture of the loss for this particular choice of car quantification. And I can follow that up by looking how good the... Just make it unbearably complicated. I have now copied in black all the centroids on a separate transparency. See, this is what I've done. I've computed the centroids and I've copied them in black. So these are the centroids of all categories. These are the...
You've made up 2 initial arbitrary quantification stage.
No, I've just made an initial arbitrary choice for the car quantifications. And I've computed the corresponding optimal category quantifications because these are the centroids. Yes. And now I have a quantification of the centroids which was computed from the original arbitrary car quantification. And now I'm going to look how good this quantification of the categories is. And now I must not look column-wise, I must look row-wise. So what categories of variables is the Chevrolet's Chevette in? It's in category 1 of all 3 variables. So here are the categories 1 of all 3 variables. If you take the centroid, these two actually coincide. If you take the centroid of that, then you find that they're pretty close to their centroid, which is the new position for the Chevrolet's Chevette. You can do the same thing for the Dodge Diplomat. That's the other one I've selected. It's in category 2 of variable 1, which is up here. It's in category 3 of variable 2, which is down here. And it's in category 2 of variable 3, which is down here. Again, there's not too much loss here. And you can take the position of the centroid as a new position for the Dodge Diplomat, as the improved position for the Dodge Diplomat. And I've done it on the right here for the Oldsmobile 98, which is in these 3 categories, and which is also fairly close. Yes. Now this is, in the first place, it shows you a picture of the loss, because this is the loss function which shows you how good the quantification is, and in this time in terms of the rows of the matrix. The previous one was in terms of the columns of the matrix. It also shows you in a sort of a extra bonus type of way how you would go about improving the quantifications. And this type of improving, which is sort of an averaging process, is the basis of the actual algorithm we use in homogeneity analysis, which I will talk about after the break of 10 minutes.